here's your student password. I'm assuming you probably have to uninstall your own, what you have now, download the new one, and reinstall it. You might be able to update directly without uninstalling and installing. I have no idea. I haven't done it yet because I wanted to have the same thing as of today, but I'll do it through the week. So I'm assuming from next week on, we'll have the newest version ever. So this is good for a year. So throughout the year, they're promising they're going to release SMS 12. So you guys are allowed to update with the same license to SMS 12 whenever that becomes available. That means we have, state of the art here. And here's the instructions. So this is on Blackboard. Okay. So what we're going to do is we're going to have a little chat on geospatial parameters, most common ones. And then I'll see how much I can show you from this machine, and we'll go to the lab and we'll work there. So we're going to adapt a little bit. So as I said, we're going to talk about geospatial parameters, and those reside on the file that's called Fort 13. So we're going to have a class, entire class about the Fort 13 file. So we're adding an extra file to the mix, the Fort 13. What the Fort 13 file does for you is it carries your geospatial parameters. And the reason I keep calling them geospatial parameters are they are spatially dependent parameters, which means each node gets a parameter associated to it. So there are parameters that are unique for the entire simulation that are not spatially varied. Others might vary over space, therefore we use the Fort 13 file to add a parameter per node. So the first thing we want to use those parameters for is to incorporate now land cover into our simulation. So I have a picture here of a given land cover. So you see here the open coast, dunes, wetlands. It could have been any environment that we're trying to model, the wetlands, for example. So we wanted to have parameters that we can incorporate those into our modeling framework. And if we go back to our first class, and if you think a very schematic thing here, flow over vegetation or any other obstacle, there's going to be an impact to the amount of momentum that gets transmitted to the water column from the wind. So remember, wind was one of our major forces. Now if there's vegetation, or if there's a building, or there's something that does not allow the wind vector to move the water, we wanted to account for that. There's also the friction drag at the sea bottom, which will try to reduce the water from moving. Mm-hmm. So, can I go back? I can. So if you think about it now, we wanted to have a different friction value for here, and for here. That way our simulation is more realistic. What we were doing before, we said, yeah, it was just all the same. That's what you guys been doing so far. So today the goal is to incorporate this into the model. So the way we do that is we incorporate a frictional drag at the sea bottom term that would act into your momentum equations. Mm-hmm. That you can choose which formulation you're using for your bottom shear stress. There are different ones. The most commonly used so far is the ones that incorporate the Manning-Zan parameter. So if you remember from hydraulics, Manning-Zan is parameter, non-dimensional parameters that will give you a sense of how much friction you will get.
Reynolds number.
No, Manning's number. Different than Reynolds numbers, are different things, another thing. There's the Froude number, there's the Reza, there's a bunch of them.
Yeah.
This one is the Manning-Zan.
Okay.
The same thing with the transfer of momentum from the wind to the water. There's basically two ways we're going to deal with the wind in ATSERC. One is we're going to say there is wind momentum transfer or there's not. It's a binary condition. So if that given space it's rigid enough or it's blocking the wind enough that there's no transfer whatsoever, we'll block the wind completely at a given node. So if there's a building, like here, this entire building. And you know, in that part of our mesh, there shouldn't be any transfer of momentum from the wind to the water. Shouldn't even be water, right?
It's gonna go around, right? It's like,
Around is fine, because remember
like
those
eddies
those
and
are
stuff, like little wind eddies, right?
those are spatial parameters. So we're talking about a per node thing.
Okay.
So now we're transitioning from one number to each node in the numerical mesh. So remember your mesh, each dot gets a parameter. So here we're saying this dot, at this dot, there's no transfer of momentum from the wind. Or if you're thinking about friction, this dot has a friction of this much. And the other way we're going to do that is the frictional resistance, which is we're going to look around in a radius from this node. In every direction, we're going to say, you know what, in 5 kilometers away from here, there's this kind of line cover. Therefore, by the time the wind makes its way to me, it got reduced by some amount. And we do that at 360 degrees. Oops, too fast. Now, how do we go from our mathematical formulations to reality? There are several land cover data sets out there for the US. I have here the 3 most common ones: the National Wetlands Inventory, National Land Cover Data Set, and the CCAP, Coastal Change Analysis Program. Those were done for several years. So within these data sets, there are a variety of years that are available. And LCD is already on 2015, so there's more than what I have it here already. So those represent our best guesstimate of the land cover spatially for a given year. Or not our, but theirs. So each program has its own thing. There are also global data sets. So if you're working globally, you can get a global data set that will do that for the entire world. So either or. There's a resolution issue here. There's a format issue. There's several things that goes with each of those. So who chooses that? You do. It's whichever suits you better, whichever you want to work with. So in reality, how we do that? There's a setup that I had from an ArcGIS framework I developed, but the concept is kind of the same. We would start with the land cover data set that has information about land cover, so let's say forested, mangroves, high developed, low development, all those things that come with a land cover database. And we would have a lookup table that will give us information for the parameter we're trying to estimate. Let's say Manning's End. So if you don't remember about Manning's End, what Manning's End gives to you is a non-dimensional number that assigns a frictional value, non-dimensional frictional value, to a given land cover type. And that's done based on observations, and you know, in the past people looked at streams, so this comes from the river hydraulics, and they said, you know, forested area would have a Manning's End of 0.15, and a marsh would have a Manning's End of 0.04. So you know, there are non-dimensional numbers that goes with the land cover classes. Therefore, we have what we call a lookup table that relates land cover class, Manning's End. Once we have that, we can create what I'm calling here a parameter raster, which has information of Manning's End over space based on the land cover. The next step is we wanted to combine that to our finite element mesh, because that's where we're solving the shallow water equations at. Remember the mesh, the nodes? So each node needs to get a number. So in order to do that, there are algorithms that will look at your node, look at the land cover around, and we'll decide which value that takes. There's a scaling issue here, because your mesh might be, you know, one node every 500 meters spread around, and your land cover data set might be a 30-meter DEM. Therefore, you need to, you know, average out everything around to get a one value. Or it might be the other way around. You might have a global data set that is 1 pixel every 10 kilometers or 1 kilometer. And you have a 30-meter resolution mesh. Therefore, it's all the same number for a lot of nodes. So it could go either way. You guys see that? So we need an interpolation extrapolation scheme that will combine the location of your node to the parameter you're trying to assign. And here I proposed at the time an area average using in polygons. We won't get into that. I'm happy to talk more about that if that becomes the thing. But do I have an animation here? It's kind of hard to see, but in this map here, and I have some more slides about this work we did at Corpus Christi Bay. This is in Texas. Here, I have the representation of my nodes. It's hard to see here because I have lots of nodes, but if you look at here, you can see the dots. So this is representing my mesh.